So as you guys are finishing up with that chapter one test, and before we go into our little section with your analysis, part of that's going to be going through and testing organic macromolecules, which deals with bonding. So this also should be real quick one day for us as we move through. What you guys are going to see is some stuff on basic chemistry. So just going through it super duper quick. You guys will see a copy of your periodic table, so it will help you with a worksheet or two that you guys will see along the way. And what you guys are going to see on that periodic table are your elements. So basic substances in nature, which can be subdivided by ordinary chemical means, meaning basically everything on that periodic table is an element. It's made up of all the same type of atoms put together, making up that particular element. You guys should know that there are 92 naturally occurring elements. Anything above 92 is basically synthetic elements, meaning that they're man-made. Usually they're going to be very unstable as well. In chemistry, you guys probably went through, you divided your periodic chart or your table, your metals, your nonmetals, your gases. I'm not too worried about that, but you guys should be able to identify some of them. Your metals, your sodiums, potassiums, calciums, things like that in that particular column are ones that can form cations. So cations are positively charged as opposed to your anions, which have a negative charge to them or a negative ion. That usually comes through ionic bonds, which means they're giving or taking electrons. You guys will see that in a little bit here as well. But they like to ionically bond, unlike your water molecules that we talked about that we'll go through, and they covalently bonded together. You should know your sponge elements, and that's important with biology because those are the six most common elements in biology. So if you think about sponge, we have sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen. And it's that carbon molecule that we're going to come back to and really hit up with organic chemistry. And anything that's considered organic usually will contain or should contain the element carbon. Are there exceptions to the rules? Always carbon dioxide, for instance, is not considered organic, even though it does have carbon in it. Elements are composed of atoms, and atoms are that smallest part of an element that can exist and still have the properties of that particular element. And I said, don't confuse element with cell. Cells is the smallest part of a living thing. Atoms is the smallest part of an element, or smallest part of some sort of material or nature, something within nature. If you guys split apart that atom, you guys have your subatomic particles, protons, neutrons, electrons. Know where they are, know what charges they have, their masses to them. So you guys see them here on that chart. Within the center of your atom, you have, or the nucleus of your atom, you have protons and you have neutrons. That is where all the mass of that particular atom is going to be found. It's within the nucleus, which is why our atomic mass unit for a neutron and proton is going to be 1. Electrons do not have any mass, but they're taking up all the space of that particular atom. So if you think like a big baseball stadium, and you go over and you put a dime right on that second base, and you say that second base represents my nucleus, that second base is going to have all your mass. But taking up all the space, taking up the infield, the outfield, all the stands is where those electrons are going to be found. So the electrons are taking up all the room within that particular atom, even though the mass is going to be within that nucleus is taking up all that mass there. Charged neutrons are neutral. There is no charge on them. Protons are positive, and electrons are negative. It's the protons that are going to determine which atom that we're looking at. So as you look at atomic number on your periodic table, that represents your number of protons. So anything on the periodic table, protons are going to equal electrons because they are neutral elements that you guys find there. So if carbon's got 6 protons, it's going to have 6 electrons. It's not until we start bonding and we start creating these ions, both cations and anions, that changes just a little bit. Remember, if we change our number of neutrons, though, we then create an isotope. So if we change our number of neutrons, we're not changing the charge of it because neutrons are neutral, but we are changing the mass of that particular element or that particular atom there. And usually as we keep increasing it, you can often make it radioactive. So radioactive carbon, we can actually begin to start changing that and making it more and more radioactive. And that's how they do dating of fossils, is using radioactive carbon because it's got more neutrons added to it. You will never ever change your number of protons. If you do, you're going to change the element that you're looking at. If you change your number of electrons, either add or take away through bonding. then that's when you are going to create that charged atom. You're creating some sort of ion, and we're going to see that more when we go through gel electrophoresis, because we're forming these charged atoms, and that's kind of what's getting pulled through electricity there. So we know that they're arranged on the periodic table by their atomic number. Once again, their number of protons. Know that the atomic number is number of protons. Your atomic mass is what you find in the nucleus, so it's protons plus neutrons. So if you're looking at this area here, all those little black circles, those would be protons. My white circles would be neutrons. How do I know that? Black circles have pluses on them. I know protons are positive. I know protons and neutrons are found within the nucleus there. So that's what we have there. My outer shell are my electrons. So are my clouds, my orbitals, my energy levels, however you want to identify them. Your outer shell are your valence electrons, which means that those electrons that we find in that outer shell, they're the ones that are going to be available for bonding. So, starting in the beginning, the first ring that you have around that nucleus can hold 2 electrons. Each ring after that, in terms of biological terms of bonding and how things are able to bond in biology, we say that every energy level or every cloud or orbital outside that first ring can hold up to 8 electrons. The thing is, you have to fill the previous ring before you move on to the next. So I put 2 in the first. Here you can see that I have 4 in the next one. It can hold 8. I only have 4. That means that particular atom that we're looking at here, element that we're looking at here, is completely unstable. So it wants to go through and find 4 more electrons or give away these 4 electrons so that we are able to stabilize it and have a full outer ring. Once again, those valence electrons, I only have 4 there. I want 8. If I went through and said make an isotope of this particular element that you guys see here, you would just go, oh, well, I have 1, 2, 3, 4, 5, 6 neutrons there. So let me take away maybe this neutron, or let me throw a few more neutrons in there. That's all you're doing is just changing the mass. I'm not changing protons. That would give me a different element. I'm not changing electrons. That would change the charge of that particular element, which is making it heavier or lighter. Okay. Radioactive isotopes are useful in treatment of diseases. We can use them to treat cancers. We can actually track them through the body. Cardiovascular trackers, so they can get things. They're kind of like considered what we say is hot. So they can use a tracer to see where it goes. Are there any blockages anywhere along the line? Anything with the digestive system. We can pinpoint certain cells, cancer cells, or certain cells within an area, and use that as treatment. So we're doing a lot more with these radioactive isotopes than we have before. Electrons, we said, are in the outer ring. They're outside the nucleus. They are moving at high speeds of light, tons and tons of energy that we see here. We usually just show them as being stable, as what you see in the diagram above. So we say that the space outside the nucleus is about 1,000 times the diameter of the nucleus, which is why I said think about that dime on second base of a big old giant stadium. And that dime is the nucleus. Everything else, infield, outfield, the seating of the stands is all where the electrons are going to go. So we have up to 7 energy levels there. We say the first one holds 2 electrons. Everyone after that can hold 8 electrons. Only those electrons in the outermost ring are the ones that are going to be available for bonding. We said those are the valence electrons. And why they're important is because if we start bonding, we're going to create compounds. So compounds are substances composed of 2 or more elements chemically combined. So not physically combined, but we are chemically combining them. We are bonding them together, and those bonds are going to store energy. So one of these bonds we've kind of already looked at. You guys created water. It's a polar covalent molecule. We take oxygen, we take hydrogen, we bond them together. The other type of bond that we're going to look at here is ionic bonds. So instead of sharing electrons like we do covalently, we're going to give or take electrons, and that's going to be my ionic bond. And that's where we're going to create these cations and anions. So first one, ionic bonds, electrons are lost from one, donated to another. So if we're looking at sodium chloride, table salt, ionic bond, ionic compound, sodium is here. If we're looking at it, we have 1 extra in the outer ring. Chlorine's got 7 in the outer ring. It wants 1 more. So what's it going to do? Sodium goes, whoa, I am super, super unstable. I have that 1 electron out there all by itself. I want to get rid of that 1 because I want to make sure I have 8 in the outer ring. So if I slide this 1 over and I give it to chlorine, I now have 8 in my outermost ring here. Chlorine, which had 7, is picking 1 up. It now has 8. But what that does is it changes the charges of these particular elements. Sodium does not have the same number of protons as it does electrons anymore. Remember, I gave an electron away. So it actually has one more proton than electron. It has one more positive than it does negative. So it has a positive charge. That sodium is known as a cation. Your chlorine is known as an anion. It is a negative ion. So a positively charged ion is known as a cation. A negatively charged one is known as an anion. So here we picked up one. We have one more electron than we do proton. So it has a negative charge to it. You can also do it with magnesium oxide. Same thing, but you would see a +2 charge on magnesium. Oxygen gets a -2 charge there. So you can always try that one on your own if you like, and I can go through it if you would like. Ionic bonds, we know that they form between two ions, so it's a charged particle. We either lose or gain them. Ions are attracted to each other, so that cation and anion. It's kind of like batteries. Opposites are going to attract, and that plays an important role when we get to gel electrophoresis. Best way to think about it, cation. Cat's got that T in there. So think of that T as positive. So cation is your positive ion. Anion's got the N for negative. So an anion is a negative ion. So if you are a positive ion, you have one fewer electron than proton. If you are an anion, you have one more electron than you do proton. Do not ever change your proton number. That identifies the element that you're looking at. If you start changing it, you're going to change your element. Ionic bonds, when they form, they usually form crystalline structures. Think like table salt. Okay, that's a huge ionic bond, sodium chloride. Common ions that we see within the body, not only sodium and chloride, but also potassium. Major electrolytes, they maintain composition of body fluids, such as sweat, such as blood, such as tears. Calcium, sodium, chlorine, they help with nerve impulses. So if you've ever seen like those marathon runners or triathletes and they're running that last little bit of the race and they fall down and they look like they want to get up and they look like they know what they're doing, but they can't quite get there, their ions are messed up within their body. So they've sweat out all these particular ions and their nerve impulses are not working the way that they should. Their muscle contractions are not working the way that they should. So they're not able to kind of get through and do what their mind is trying to tell them to do. Their muscle action's not quite working the way that it should. We also have other ions, magnesium within your chlorophyll. We have iron within your hemoglobin. And this hemoglobin is actually the oxygen component, carrying component of your blood. So when you have low hemoglobin or you have low oxygen levels within your blood, you're very tired, maybe you're anemic, it's because of that iron level, that ion that you have within your blood is a little bit low there. Usually these ones are solid, they have high melting point as well as high boiling point are some characteristics of them. Covalent bonds, when electrons are shared by two atoms. So we are sharing of electrons, overlap of electrons. This is what we saw with water. We said that hydrogen and oxygen, we're going to go through and share it. You guys see it down here. We talked about polar covalent molecules, and we said there was an unequal sharing of those particular electrons. So even though they're sharing them, oxygen kind of hogs some of those electrons. It makes it slightly negative. If you are a non-polar covalent bond, everybody's sharing equally, everybody's sharing nicely. O2, oxygen, for instance, when oxygen bonds to other oxygen, they're sharing two pairs of electrons there. It is a non-polar covalent bond. It is a linear structure, and they are sharing those electrons evenly there. Unlike what we see with water, which is what kind of creates those Mickey Mouse ears, because oxygen pulls those electrons down, and instead of being linear, those hydrogens kind of get pulled up because they are slightly positive there. And that's what creates those dipoles that we see. You can also try it with methane. Methane is actually a non-polar covalent. Carbons in the middle, we have 4 hydrogens all the way around the side. We'll actually see that when we get to organic chemistry. Things that you guys should know about bonds. We talked about this with anabolic and catabolic reactions. So when you create a bond, energy is stored in there. So we said think about anabolic reactions, think about photosynthesis. Plants are taking carbon dioxide, they're taking water, they're taking some sunlight. They're creating bonds and they're making glucose, and that glucose is made into maltose, and that maltose is made into a very large polysaccharide. And as they're doing that, we are creating bonds there. And there's potential energy stored in those bonds, so that when that plant gets eaten, where that plant begins to break down some of its food for cell respiration, and we break those bonds, then we are getting that kinetic energy, that energy of motion. So when you create a bond, you're storing energy. When you break a bond, you are releasing that particular energy. Mixture is a physical combination of two or more substances as compared to a compound in which atoms exist in a fixed ratio. They still maintain or retain their identity. So think about like sand, if you mix that, that's a mixture. Salt and pepper, if you put it together, that's a mixture. Salad, you can throw all these pieces together. It's still a mixture. They're not blending together there. They can be separated by physical means. So that ink that we had within your chromatography, that was actually a mixture. So we were able to separate it out and we were able to pick out those particular parts there. A solution is a homogeneous, the same throughout. So homo means the same. Homogeneous, we're talking about that mixture being the same all the way through. So salt water, you mix it up together, you've got that equal combination of salt and water. Eventually it may settle out. So in that particular part, we talked about this with water. The solute is the substance being dissolved. Solvent is the substance that's doing the dissolving. Water, once again, that universal solvent. It is breaking down that ionic compound. It's a great dissolver of ionic compounds, and that would be salt. If you are soluble, you can be dissolved in a solvent. If you're insoluble, and we'll talk about lipids and how they're insoluble, such as water, they cannot be dissolved in a solvent. We went through qualitative, quantitative. If you need to, it's on there again, but we did that within our first section. This you can kind of flip around if you guys want, but it's just pulling one of your elements off the periodic table and know how to read it. So if I did carbon, I see the numbers 6 and 12 there. They can vary depending upon what periodic table that you guys see. Usually your smaller number is going to be your number of protons. It's also your atomic number. It helps identify what element we're looking at. They're the ones that go in order on the periodic table. It's not always the one that's on top, but you'll be able to tell because the other number is usually going to be a decimal point number that you will either round up or down depending upon what number it is. So here for carbon, we round it to 12. That 12 represents the atomic mass. That atomic mass represents everything we find in the nucleus. So that would be your protons as well as your neutrons. So I know that my atomic number is 6. My atomic number also represents my number of protons. So by looking at that, I can be able to determine the number of protons, neutrons, and electrons. Anything on that periodic table is going to be neutral. So I know that my protons as well as my electrons are going to equal each other. Positives and negatives will equal each other. If I have 6 protons, I have 6 electrons. If my mass is 12, and that mass equals protons and neutrons, 6 plus my number of neutrons gives me 12, I know that I have to have 6 neutrons as well. They're not always going to be even, 666, or numbers the same all the way through. Okay, just so that you guys are aware. The C in the middle represents the symbol. We usually have the word there too and tell you what that represents. The example below it, you're going to see C614. That is if I was creating an isotope. So what's happening there? My atomic number is still 6. I still have 6 protons. You cannot change that. If I change that, I'm changing my element now. The bottom number, the 14, has been changed. So what that means is that now I change my number of neutrons. I've added 2 neutrons there. It's heavier. So that particular carbon-14 is what we use for radioactive dating. Carbon-14, we can use it to date fossils. So it's heavier. 2 more neutrons have been added. I know I still have 6 protons, which gives me 8 neutrons there. Electrons don't change. It's still neutral on that periodic table. Okay, so go through some examples. You'll see some of this stuff on your notes as well. You'll see some examples and some practice problems. If you are not sure, find a time. We can Google Meet. We can go through some of this stuff in class if you're here in class. This is just the beginning part as we work our way into organic chemistry because you're going to see that bonding there and those structures and double bonds and single bonds and triple bonds. We make sure that you understand what's going on with those bonds and where that energy is coming from. So once again, if you guys do not understand what's going on, please come see me, set up a time. We can Google me, we can chat, whatever else. Okay, thanks.